Now let's start with the next topic, that is the electrostatic potential due to system of charges. Okay, till now we have considered two charges, one charges, and with respect to that we found the electrostatic potential. But now we are going to consider that there are many charges, and with respect to that many charges we have to find the electrostatic potential at any point, let's say P. Now in this diagram there is a point P. Okay, now here we have to find the electrostatic potential, and there are various charges around it. That is, let us suppose there is a charge Q1 which is placed here, there is a charge Q2 which is placed here, Q3 is placed at this point, Q4 at this point, similarly Q5 at this. I mean, there is no particular fixed pattern in which these charges are aligned. These charges are randomly aligned in a particular space, and with respect to these charges we have to find the electrostatic potential at point P. Now it is given to us that Q1 is at a distance R1 from the point P. Similarly, Q2 is at a distance R2 from the point P. Q3 at a distance R3. Similarly, Q4 is at a distance R4 and Q5 is at a distance R5. So this is given to us, and now our work starts from finding the electrostatic potential for Q1, Q2, Q3 and so on. Here I have taken only 5 charges because I feel like taking it. You can take 6 charges, you can take hundreds of charges, it all depends upon you. Okay, I am going to give you the expression for number of charges. Let's say n. Small n represents the integer value, that is, it starts from 1, 2, 3 and continues. Okay, now if I am talking about the potential with respect to the charge Q1, so the formula for it is 1 by 4 pi epsilon naught Q1 upon, what is the distance of separation? The distance of separation is R1. This is our equation number 1. Similarly, V2 is the electrostatic potential due to the charge Q2. So it becomes Q2 upon R2. This is the second equation. And similarly for V3, 1 upon 4 pi epsilon naught Q3 upon R3. This is the third equation. Similarly, you have to find electrostatic potential for fourth and fifth charges also. So these all are the potential which are calculated with respect to Q1, Q2, Q3 and Q5 charges. Okay. In this particular case, if I am applying the superposition principle, so at point P, I need to add all the concerned electrostatic potentials which are created by the individual charges. Okay. So if at point P, that is the total potential, if I have to find at point P, so it becomes V1 plus V2 plus V3 and so on till Vn. Here Vn is V5. Okay, now just add all these values. Now I am going to take the common term outside the bracket. The common term is 1 by 4 pi epsilon naught in all the 5 equations. And what are the non-common terms? It will remain inside the bracket. That is Q1 upon R1 plus Q2 upon R2. Similarly, it goes on and on till Qn upon Rn. Qn upon Rn in our case, in this diagram, what it is? It is Q5 upon R5. Now, if I have to simplify this whole set of expression, then I have to use the sign which is called summation. The summation, what it does, it provides a certain loop. In that loop, whatever the value comes, it keeps on adding. Then the loop also get incremented by 1 step each. Now, let's see how the summation is done. 1 by 4 pi epsilon naught constant. If I put a summation sign is represented like this, and the loop which I am talking about, let's say I represent it by I. You can take as J, you can take as K, somebody takes R also. Anything you can take for the loop incrementation. Now, our initial value in this particular condition which keeps on incrementing, okay, we have to take only those values within the summation sign that keeps on incrementing. The value that keeps on incrementing are Q1, Q2, Q3. Similarly, R1, R2, R3. So Q upon R is taken into consideration within the summation sign. So we are going to take Q upon R. Now, It starts from the value 1. That is, what is the initial value? It is 1. So, the initial value of I becomes 1. So, similarly, it goes on, and what is the final limit? The final limit is small n, which is an integer value. So, you have to represent the final limit also on the summation, that is small n. The summation shows you that the I, which is a loop, starts from the initial value 1 and it ends till the final value, that is small n. Now, we are going to assign Q of I and R of I. This is how it is shown. You can see, you can check also that whether this formula is correct or not. In the first condition, when my value is 1, so it becomes Q1 upon R1. Okay, we get the answer. Similarly, it gets incremented by one step, as I've already told you. So, the next step, I becomes 2. So, it becomes Q2 upon R2. Okay, the next step is also fulfilled. Similarly, Q3 upon R3, Q4 upon R4, and what is the final step? Final step is N. So, when the value of N comes, I becomes is equals to N. And when we put the value of N here, it becomes Qn upon Rn. So, that means the formula that we have formulated is 100% correct. So, this is the electrostatic potential when I talk of system of charges. Now, moving on to the most important topic, that is equipotential surfaces. Now, let us understand what is this equipotential surfaces. Now, as the name suggests, equipotential surface, that means it is basically a surface where at all particular points the potential is same. So, what is equipotential surface? This is a kind of surface where the potential is same at all points. Now, in order to explain clearly what is this equipotential surface, now let's move on to the formula. What is the formula for the potential? It is given by Q upon 4 pi epsilon naught R. Now, this is the formula for the electric potential due to the point charge object. Now, if I consider the point charge object, in that condition, what is the equipotential surface for it? If there is a point charge, let us say this is a point charge which is represented by small q as in the formula. If I have to make a equipotential surface, then this equipotential surface is a region of sphere which is surrounding the charge at all points equally. Now you can see in the diagram, the point charge is at the center and the sphere has a radius r. Now this radius r, it's same as all points. At this point also this is r, this point also this is r. That means if we have to find the potential at this point, okay, at this point, at this point, at this point, at all points you are going to get the same formula. That is, at this point also you will get the value of V. At this point also, at this point also, and at this point also you will get the same value of V. So we can conclude so that for the point charge, the equipotential surface is a sphere because we are getting the potential same at all point of the surface. Similarly, here I have mentioned the word surface. Now, if I ask you that what are the equipotential surfaces, then in that condition there will be more than two surfaces. Now, if this is a point charge, let's say Q, and if I draw another sphere, okay, this is another sphere, a larger one that surrounds the smaller sphere. For the same charge which is placed at the center, the radius of the outer sphere is, let's say, R1. So, if I talk of every point at the surface of the outer sphere, then the radius will become R1, R1 here also this is R1. That is, if the radius is R1 for one particular point, then for another particular point also the radius is R1, the radius is R1, the radius is R1. So, we can say so that for this second second sphere. At this point, if you are going to find the electric potential, this is V1. At this point, you are going to find this is also V1, this is also V1, this is also V1. So, these are called the equipotential surfaces for the point charge which is placed at the center of them. Likewise, if you take more than 2 or 3 spheres, these are the spheres, and we keep on adding all these spheres, so they all become the equipotential surfaces for the point charge body which is placed at the center of all these spheres. So we can say so that for point charge body, the equipotential surface is spherical. Now, let us consider the case when there is a line charge body, okay. If suppose this is a line charge, okay, a line that consists of charge at various points. For this line charge, what is the equipotential surface? That is, I am talking about such a surface that if we place that surface encircling this line charge, then at all points you will get the same electric potential. So in this condition, it will be cylinder. Okay. So for line charge, if I talk about, then I am talking about the cylinder. Now you can see here, if I talk of this point, then this point is also R. If I talk of this point, then this point is also R. Similarly, this point is also R. If in this circle I am coming, so every point you will get R. If the distance is same, the charge is also same, it is uniformly distributed over the particular line, so Q upon R is same. That means you will get the same value of potential at every point. So we can say so that for the line charge, the equipotential surface is a cylinder. Now, let us consider the sheet of charge. Okay, like for example, we have the paper, my hand, okay. Let us suppose this is a paper. This paper is considered as a sheet, okay. If the charges are distributed over the sheet of charge, then let us find out what is the equipotential surface for it. If this is a sheet, okay, and I am asking you that all the charges are uniformly distributed over the sheet of charge. In that condition, what is the equipotential surface? The equipotential surface is also a sheet which is placed in parallel to that of this sheet of charge. How it looks like? It looks like this particular diagram. Okay, you can see here that this sheet which is placed in front of the sheet of charge is considered as the equipotential surface. Similarly, if we are going to place 1, 2, 3 and many more sheet of charges, if I am going to place parallel to each other, in that condition they all become a equipotential surface for this sheet of charge. If it provides the electrical lines, then these electrical lines come at a particular angle and it passes through all equipotential surface, and at every point if you talk about, you will get the same value of the electric potential. So these are also called the equipotential surfaces for the sheet of charge. Now, this is also the equipotential surface in the case of first electric dipole, that having positive and negative charges. Similarly, this is the equipotential surface when the two charges are of same polarity. Now, the positive and the negative, they have the tendency to attract each other. In that condition, the equipotential surface has a much denser line towards each other. That is, if you look at this particular portion, if you look, then here the equipotential surfaces are more dense, and if you look at this particular portion, the equipotential surfaces are rare, that is, they are less dense and apart. So this shows that the tendency of the equipotential surface for the positive charge is towards the negative charge, because they are heading towards each other. Similarly, for negative charge also, you can see that the equipotential surface at this particular region is dense, and at this particular region you can see here it is not dense, that is, it is rare. So it is moving away from the positive charge, so that portion is less dense, this is coming towards the positive charge, and this shows the attraction between the two. So this is the equipotential surface for positive and negative, that is electric dipole. Similarly, if I talk about the two positive polarity charges, in this condition, these two have a tendency to repel each other. Now, if you look at this particular portion, then here it shows that the equipotential surfaces are less dense as compared to this particular portion. This portion is much more closer as compared to this portion. This is less dense, rarer, and this is more dense. Why it is less dense? Because it has a tendency to repel another positive charge. So the equipotential surfaces are less dense. Okay. Similarly, in this condition also, the equipotential surface in this particular portion is rare, less dense. That's why the equipotential surfaces are apart from each other. Similarly, at this point, you will find that the equipotential surface is more dense. So by the equipotential surface, it gives you the visual representation of the attraction and the repulsion between the 2 point charges. Now let's come to the properties of the equipotential surfaces. The first property of the equipotential surface is the work done in moving the charge on an equipotential surface is zero. What we have studied that this is point A, this is point B. Okay, if there is a charge, let's say Q, and it has to move from point A to the point B, so there is some work to be done. So the work done is given by a formula, that is WAB. Because why AB? Because the charge is moved from the point A to the point B, and it is given by the formula which is equals to Q, which is the charge, into VB minus VA, that is delta V. Delta V means the potential difference. So in this condition, the B point is at higher potential and A point is at lower potential because the charge moves from A to the B. So it is VB minus VA. Now, if I talk of the equipotential surface, so in that condition, this AB, this point AB, this lie in the equipotential surface. So this is the equipotential surface in which the point AB lies. So in that condition, when it becomes an equipotential surface, at all points you will find the same electric potential. That is, if we talk of VA or we talk of VB, both have the same magnitude. So VA is equals to VB. In this condition, if VA is equals to VB, so they both get cancelled out and your answer, that is work done, is equals to 0. So this is what we have to prove, that work done in moving the charge from one point to the another on an equipotential surface is 0. Now let's move on to the second property. The second point is that the electric field is normal to the equipotential surface. Now, if the electric field is normal to the equipotential surface, so that means that the angle between the E and the area, that is the plane surface, is 0. So, if suppose this is the equipotential surface, okay, so in that condition, the electric field vector should be always 90 degree with respect to the plane surface. So, we have to prove this. How we are going to proceed? Let's see. Now, in this condition, let us suppose this is the equipotential surface and the electric field vector is making an angle, let's say theta, with that of the plane surface. We are not considering in our derivation that the electric field vector is perpendicular to the plane surface. We have considered that it is making a particular angle, let's say theta, with that of the equipotential surface. Now let's move on to the proving. So dW is given by F dot dl. This is all what we know. F. Okay, if we expand and take the magnitude, so it will become f of dl cos of theta. Yes, it will become. So this is your dw. Now similarly, what is force? Force is given by electric field intensity into Q, that is the charge. Here the charge that we are going to take is dq, very small amount of charge. So instead of force, we are going to write E dot dq into dl cos theta as it is given there. Now, you can see here that we already have proved that work done is equals to 0 when we consider the equipotential surface. So, we can equate this whole formula with that of the 0. Now, it is already given to you that there is the charge dq. If there is a charge dq, so there must be some electric field. If there is some electric field, so in that condition, this whole formula is equated to 0. So, we can write that electric field is not equals to 0. It cannot be because there exists a charge. In another condition, dq also cannot be 0 because it is already given to you that there is a particular charge on the equipotential surface. So, dq is also not 0. Similarly, dl is also not 0. dl is the distance. Distance cannot be 0 because the surface is already given to you. So, what is left? What is 0? The 0 term is your cos theta. You are left with only one term, that is cos of theta, and this cos of theta should be 0. We don't have any option in order to see that there is only one term, that is cos theta, which is 0. And how the cos theta is 0? The cos theta is only 0 when theta is equals to 90 degrees. So what is theta? The theta is the angle between the electric field intensity and the surface, that is the equipotential surface. So you can see here that we proved that the electric field is always normal to the equipotential surface. Now moving on to the third property, that is the equipotential surface of a point charge when it is placed at the center is the concentric spherical surfaces. This we already have discussed, that when the point charge is placed at the center, then in that condition, what are the equipotential surfaces? The equipotential surfaces are the concentric spherical surfaces. Concentric circles mean one into the another. So in this condition, you can see that when the point charge is placed at the center, so around the point charge there are sphere, and these are placed one into the another. So these are called the equipotential surfaces for the point charge. Now moving on to the fourth point. In the fourth point, we have to see that the two equipotential surfaces cannot intersect each other. Now, in this condition, we have to prove it by a small diagram. Suppose this is a first equipotential surface, okay. This equipotential surface has the potential, let's say V1, and this V1 is distributed at all points. If at all points you will find V1, you will get the same value of V1. So this is the equipotential surface. Similarly, we will take another equipotential surface, let's say V2. At all points in this particular surface, you will find the same value of V2. So this is the equipotential, second equipotential surface. Now, if they both intersect each other, like for example, this is the first one where we found the V1. This is the second one where we found the V2. Now you see that they intersect each other. At this particular point, you are going to find V1 at all point. At this particular area, you are going to find V2 at all point. But what about the intersection point? At the intersection point, you may get the different value of V1 and V2. It may happen that you will get the summation of V1, V2 or the difference of V1, V2. So if I talk of this whole equipotential surface, then in that condition, the value of potential is changed at every point. At this condition, this is V1. At this particular stripe condition, it is also different. It can be V1, it can be V2 or something different. At this condition also, this is also different, that is V2. So this condition does not hold for the equipotential surface, which states that the value of the electric potential should not change at any point. And here you are finding that the value of the electric potential is changing at every point. So this condition is true, and it cannot hold that no two equipotential surface can intersect each other. So this is all about the properties of the equipotential surface. Now let's move on to the relationship between the electric field and the potential. For that, we have to take two equipotential surfaces. This is one equipotential surface, okay. This is one equipotential surface, and there is another equipotential surface which is placed just below, or we can say beneath this particular equipotential surface. So these are the two equipotential surfaces which are placed like this, okay. If you join it, then these are placed one over the another. These are the two plates. You can assume it as a plate. This is one plate and this is another plate. These plates lie on this particular plane like this, one over the another. So this is one plate and on the top of there is another plate. Now let's start with the derivation. In the derivation, first let us say that this first equipotential surface has the electric potential capital V. That is, at all points we are going to find the value of electric potential same. Similarly, if I talk of this equipotential surface second one, so in that condition the electric potential value is changed and this potential value is V plus, let's say, del V. What is del V? The del V is a very small electric potential. This is capital V and this another equipotential surface which is V plus del V. Both are placed parallel to each other. Now, if let's say this is a point A and there is a point B on the second surface, okay, and there is a charge, let's say, plus Q. Now, if these two equipotential surfaces, these are placed in the electric field, okay, this is the electric field and these are placed in the electric field. What is the direction of the electric field? This is shown by these lines. So what you are seeing here, that these two equipotential surfaces are placed in a electric field vector. Now, if this is a plus Q charge which is placed at the point B, so we need to move the charge against the nature of the charge, because this plus Q charge has a tendency to move in the direction of the electric field. But if you have to find the work done, so you have to move the charge in opposite direction to that of the nature of the plus Q charge. So the nature of the plus Q charge is to move in this direction, so we have to move in opposite direction. So what is the opposite direction? The opposite direction is this. So this is the opposite direction towards the point A. Now this plus Q charge has moved from point B to the point A, and this plus Q charge, let's say, we will say it's a dq. Okay, this dq means very small charge. Now dq has moved from B to the A, and this perpendicular distance from B to the A is a perpendicular distance, and let's say we will represent it by dl. So what is dl? So dl is the perpendicular distance from one equipotential surface to the second equipotential surface. Now let's see what is the work done. We know the formula of work done, that is F dot dl. Okay, dl is the distance between the 2 points. So here the 2 points are B and A and the distance between them is dl. Now this force, okay, if I substitute it by the magnitude, so it becomes F dl cos theta according to the dot product of vector. Now what is force? Force is given by a particular formula. If you remember, then force is given by electric field intensity into the charge. Here I am talking about the charge, that is dq. So in this condition, the force is substituted by E into dq and all the values remain same, dl cos theta. So this is work done. Now this is the formula for your work done as equation number 1. Moving on to the another part, dw has one formula which is related to the electric potential also, and if you remember that formula, it is given by that work done upon the charge is given by the electric potential. So we can write here that dw is equals to dq into dv. dv is the incremental or the change in the value of the electric potential. So this is your equation number 2. Now you can see here, this is dw, this is dw. That means we can equate these two values because LHS in both the equations are same. So we can equate equation 1 and equation 2. If we equate it, so we will get E dq dl cos theta is equals to dq dv. dq and dq, both sides they will get cancelled out, and you are left with E is equals to dv upon dl cos theta. Now in this condition, let's work upon the value of cos theta. Now just see here, the charge, that is dq, is moving from B to the point A, and the electric field intensity is going from this point to this point. That is, both are going in the opposite direction. So what is cos theta? Cos theta is basically the angle between E and DL. Okay, so E and DL both are going in the opposite direction. Okay, DL is going in downward direction and E is going in upward direction. Both are going in opposite direction. So what is theta? The theta in this condition is 180 degree. So now I am going to put the cos theta. So cos 180 degree is minus 1. So on putting the value, you will get minus dV upon dl. So this is the relationship between the electric field and the electric potential. Now we can draw two conclusions from this formula. There is a negative sign. You see the sign here comes a negative. What it implies? What do you mean by this negative sign? The negative sign means that the electric field is in opposite direction. Okay, this is the direction which electric field is going, that is upward. This is not the direction if we talk about the potential. The direction should be in the opposite direction. Now just see here, the electric field is going from V to V plus del V. That is, it is going from lower potential to higher potential. But we know that charges always flow from higher potential towards the lower potential. So in this condition, this is higher potential and this is lower potential. So the electric field has a tendency to flow from higher potential towards the lower potential. So what should be the direction of the electric field? The direction of the electric field should be like this, because it flows from high potential towards the low potential, and in our diagram the direction is opposite. So that's why there is a minus sign between E and the potential. So I hope so it will be clear to you. The first tells you the direction. The second point tells you the magnitude of the electric field. Now what is the magnitude of the electric field? You can see from the formula itself, the magnitude of the electric field is given by dV. This is also represented as the magnitude. So if we need to find out the magnitude of the electric field, so it is given by the ratio of the magnitude of the electric potential upon the perpendicular distance between the 2 points. So this gives us the magnitude of the electric field. So from this particular formula, we have deduced the direction as well as we have deduced the magnitude also.